Okay, here we are. Let's begin with the solution of the yesterday review. Okay. The idea is the following. We have to swap two elements, two elements, E1 and E2 of a singly linked list. And to do this, we first need to determine which are the nodes that precede the E1 and E2. How to do this? We first need to traverse our list, searching for our elements. So while current different from tail, okay, which is the idea behind these instructions? First, I start from car. If it happens that car points at E1 or at E2, then I need to store the current position, so the current node, because it's the one I have to update in order to properly swap the nodes. So this is the first. Let me print T1 list T1, T2 list T2, and this is the first part. Identify where E1 and E2 lie. Okay. Let's say D and C. Now, before I would like to recover the print all function just to show which structure our singly linked list has. Okay, So the structure is head F C B D. So we want to skip to swap D and C. Of course, I'm not currently. This is only the initial part of the function. Okay. Oh, it's right. What's happening? At least while car different from tail, at least if a list of car T1 is car. If a list of car is equal to E2, so what's wrong? Okay. Okay, sorry. The print was inside the while loop, so as it didn't find T1 and T2 at the first iteration, it raised an exception. Okay, so now it's outside the while loop. We found that T1 is B and T2 is F. Okay, so again, remember again that we want to swap C and D. So we must update the pointer of F, namely T1, and the pointer of T2, which is, the pointer of, F and B. And of course, the pointer of D and C. Okay? It's okay?
Yes.
Two safety conditions. The first one, if E1 does not belong to the list or E2 does not belong to the list, we return false because, of course, we cannot proceed. First condition. Second condition, we must succeed in finding T1 and T2, otherwise there is no reason to go on. What we have to do? Remember, we must update the values of T1 with T2 and the value of T2 with the value of T1. Okay, which is the first step. How to do this? Simply this way. Which is the Pythonic way for swapping two values. So that L list of T1 will be what was before, what was earlier the value stored in the corresponding to the key T2 and vice versa. And we do the same thing for L list of E1. L list of E2 equals to L list of E2, L list of E1. So our code works. We may remove this print. We are not interested in 1, 2. Okay. We went back. We swapped back B and C. This was the situation before, in which F pointed D and B pointed C. And now we have that F points C and B points D. Okay, so again, granted that E1 and E2 both belong to the list, we traverse our list the traditional way. So we start from the head and search for next for pointed values. While car is different from tail, if it happens that the next element will be E1, then we store the current node in the temporary variable T1. If it happens that the next node will be E2, we store the position of the current node in T2. and we update the current node in order to skip to the next one. So car equals a list of car. Okay, if we found both T1 and T2, so if searching for left nodes with respect to E1 and E2 succeeded, then we simply have to swap these two variables. I would like to remind that if I have that x is 10 and y is 20, writing produces precisely what we need, the swap between the values of these two variables, which of course cannot be applied to a singly linked list because we need to preserve the integrity of the list. Namely, we need to rearrange the pointers that allow to link one node to the following in the correct order. Are there any questions?
No, Professor.
Is it clear for everyone?
Yes.
Yes.
Sei, 8, 10. Yandaguditi? Who is Yandaguditi? Gadigi? Gambold? Tuldur? Umutoni? Korovai? Abdul? Ruggeri? Namineni? Bimenimana? Isimbi? Okay. Is it clear for everyone what we have done?
Yes. Yes.
Yes.
Are you sure?
Yes.
Very
We're
good.
just looping through the whole list till the tail. and change their positions if we have it.
Sorry?
I'm just describing what we have done.
Okay. Yes, please,
So,
again. Yes, I appreciate very much.
okay, we just looping through the till the tail through the
Yes.
whole list, and we just if we have two of them, like
Yes.
there's a condition if T1 and T2, we're changing their positions and
Yes.
returning the list again at the end.
Yes. Yes. Very well. Thank you. Okay. If I will remember, we discussed how to delete an element, the first element from a list. Okay. Well, now, how to delete a given element from a list, if any. So suppose you have a singly linked list and you want to remove a given node E. How to do?
If I remember well, yesterday we performed the exercise of removing the element that we were.
Oh, yes, it's true.
An element on our choice.
Yes.
So,
Yes, thanks for remembering. Indeed. Yes, yeah, it is. Yeah, it is. It's precisely the same idea. We need to identify the node linked to the node we want to remove. So which is the node immediately before the node we want to remove? That's the idea. Okay? We have seen yesterday and the day before how to, okay. First of all, let's analyze the computational cost of the functions we implemented. Okay, I begin with the create function, which creates a singly linked, what we refer to as a singly linked list. And of course, we may safely conclude that its computational cost is constant in time. So it does not depend on how large our list will be. Okay, what about the function add first? This one. What's the computational cost of this function? Add first. Anyone?
meet with the rest of the list, and the more element we have, more.
Oh, yes, actually, yes. But this is an additional check we inserted. Suppose you haven't this if condition. Yes, yes, that's right. Is it clear? So let's suppose for a moment that we remove the conditional, which is only to check whether the element is already in the list, okay? If this is not the case, then we simply have these two instructions, which are not in any way related to the length of the list, to the size of the list, on elements in our list, yet we simply have these two instructions to add an element in the first position. Okay? It's okay. Okay. And now add last. Someone at home willing to estimating the computational cost of this function? Come on.
I think it's n, big O n.
Sorry?
I think it's n. We have to look through the n elements.
Yes. So its computational cost is?
O n.
Yes, big O of n. That's right. Actually, again, here there is another if with the in operator, which is equivalent to another iteration over all the elements of the list. So if we disregard this condition, then it's big O of n. Otherwise, if we consider the if as well, becomes n squared. Yes, precisely. That's precisely the case. Okay, and now the first. Would you like to contribute to estimate the computational cost?
Can I say?
Can you repeat? I didn't get. Is the same? So, which is the computational cost? Someone among at home students?
I think it's O1 because it doesn't look through the elements.
Yes.
That's why.
Yes, that's precisely the case, because you don't, I mean, there is a thumb rule which consists in, are there any cycles, implicit or explicit cycles?
No.
If not, as in del first function, then it does not depend on the number of elements we have in our list. So it's big O of 1. That's right. Then last, which is our last function. You in second row, would you like to? Big O of n, that's precisely the case. Yes, very well. Okay, so this is how to estimate. Once more, we have a very economic solution, which consists in implementing while implementing singly linked list. If you add elements near the head, so in first position, and you remove elements from first position, you have a very economic, very cheap functions, because they do not depend on how many elements composing your list you have. Okay, so you have two functions, insertion and removing from first position, constant in time, and it's very advantageous. Okay, instead, if you try to do remove, add, insert an element in an arbitrary position, if you try to insert an element at the end of the list, if you try to remove an element at any arbitrary position, in this case, if you want to traverse all the list, in these cases, your computational cost will be necessarily big O of 1 at worst. Okay? It's clear for everyone? All of you?
Yes,
Yes.
exactly.
Okay. We may also, we have seen what we may term as iterative traversal of a singly linked list, which is what we have seen a number of times. For example, when we add the last element, when we remove the last element, when we remove an arbitrary element, and so on. This is an implementation. Our starting point is the head of the leading bookmark of the list. In this case, I am doing something a little bit more refined. I am counting how many elements do we have in a list, and I am creating a list of tuples, each tuple containing the position of the ordinal position of the node and the current node. But the idea is always the same. Here we are, while car is different from tail, next is L list of car, path append K, so K is initially 1, K and next. Then we update car and we increment K. And at the end we return the path. So the idea in this case is that we have a iterative traversal of the linked list, in which we proceed from one node to the pointed one until we arrive to the end. Okay? But we may also implement a recursive traversal of a singly linked list, in which in which let's skip for a moment. What do? We have R traverse, which is the name of the function, and its arguments are the list, the path, which is initially empty, and the starting node, which is initially the head, for example, of the list. Let's skip for a moment the base case, the escaping situation. We print the length of the path. We append the starting node. This is our tuple, which initially contains only the len of. So we append 0 and the starting point, which is the starting point. Okay, and then we invoke the function itself, of course, with the same list, with the updated list of path, which now contains 0 and the starting node, and with the next point, which is the one pointed by start, so L list of start. What happens? Unless the new starting point, which is this one, is not the tail, we have a longer path which contains now one element. So we append 1 and the current node, and we invoke again the function itself with the same list, the updated path, which contains now two elements, the starting node and the current node, and the new starting node, which is the next one. Eventually, it happens that the current node will be tail. In such case, we simply print level. We append this code is nonsense. We append and finally we return path. So let's, but it's okay. Okay. Do you remember what len or path provides? Yes? Length? Yes. Okay, so I slightly updated the code you see in the slide because there was a nonsense duplication of code, as these two instructions and these two instructions are exactly the same, okay? And there is no need to repeat them. So as they are to be executed in any case, I put them outside before the if conditional and executed in any case, and limited the if conditional to evaluate if start is equal to tail, then return path, otherwise invoke the function as we have said already. This is how it works. I traverse with arguments as list an initially empty list, which is our path, and the starting node, which is our head. So this is the outcome of the print all function, the structure of the list. And we have a current node head, level 0, current node F, level 1, current node C, node 2, level 2, B, 3, D, 4, tail 5. And this is the path. So, yes, 0 head, 1 F, 2 C, 4 D, 5 tail. Okay, this is the ending iteration. This is the ending recursion of the function. Okay, is it clear? And this is how our path is being composed during the various recursions. We begin with an empty list. Then we add the first tuple, which contains 0 and the starting node. Then we add 1F, then 2C, then 3B, then 4D, then 5 tail, which is the final situation. Is it clear? Is it clear for everyone?
Yes, Professor.
Yes.
Okay. The review is implement a stack using a singly linked list as the underlying data structure. stack is. What's a stack?
Is action prototype where the first, the last element.
Sorry? Yes. How to use a singly linked list as the idea, we have seen how to implement a stack using a Python list. Okay. How to implement a stack using a singly linked list? Is it possible? And how?
I think we can combine the two functions that we have created, let's say with add first and upgrading the function then last. Because if instead of the
This is a stack.
and we can use the two functions that we have created for linked list.
Which one?
Add first.
Yes.
And then last. But instead of
no, then last can be used to implement a queue.
We have to use delete first for make a stack.
Sorry, Lester. Again?
Yes, I was saying that we need to use the function del first to make a single list a stack.
Yes, that's right. Okay? Okay, go on. Actually, you have all ingredients. You simply have to put together how to create a stack, how to add elements, how to remove elements, but note that you have to return the elements. Okay? If you are implementing a stack to manage a stack of dishes, you don't want to break the dishes. You want to use them, okay? And to print. So you have all ingredients. Are you done? Okay, this impossible review required only copying and pasting the functions we studied so far. So simply copy and paste, create. Copy and paste, add first. I simply renamed as insert. Instead of taking photos, you should try and understand what I am speaking about. The del first has been renamed as extract, and instead of returning the list, I simply return the removed element, which is what we need, and print all is the same as yesterday. So I create a single list called stack, and these are 3 insertions. So what's happening? 10, 5, 7, 3. Print. 10, 5, 7, 3. Oh. Okay, now it works.
I've done it in a similar way. What I've done is just creating the new function that instead of del first is named return first. And first I'm returning the value and then I'm deleting, but it's the same thing.
Yes, but you have to remove the element from the stack.
Yeah. But first I'm setting the value of the returning value and then I'm deleting.
Okay, is it okay for everyone?
Can you just show me how you did
Yes.
Yes, Professor.
How did you modify the first with the
I simply return the x. That's all. Okay. Next topic, which is generalization of linked list, is related to doubly linked list, in which we have nodes composed of a value and 2 pointers, one to the previous node and one to the next one. So in this case, we must maintain 2 pointers. Of course, we have 2 special cases, which are the head, which has no previous pointer, which has a previous pointer to none, and the tail, which has the next pointer to none. And unlike the singly linked list, insertions and deletions at arbitrary positions can be carried out in big O of 1. So we have always operations in constant time. And we still maintain 2 bookmarks, the leading node and the trailing node, as before. This is a picture in which, as you may see, you have a value, which in this case is the acronym of an airport, JFK, PVD, SFO, and 2 pointers, next and previous, next and previous. This greatly helps in traversing the linked list in both ways. You can start at the head and go to the tail, and vice versa. You may start at the tail and going backward to the head of the list. Okay. So this is how to create. We still have a dictionary, an empty dictionary, but now the values are not the pointers of the next elements. Rather, we need a more complex structure, which is another dictionary, which contains 2 pairs, previous and next. So, this is how to we create the list of head. Is a dictionary with 2 pairs. The first one, previous, none, because on the left of the head there is nothing, and next tail, whereas so what's the result? The result is that we have an initial step two values in our two elements in our dictionary, which are the head, which is the key, to which correspond the another dictionary containing the previous and next pointers, and the same for the tail. How to access the pointers of the head? Any idea?
The pointers of the head.
Yes. Suppose we need to print the next, the prev first.
Chat notation, maybe.
Sorry?
Maybe using dot notation. Can we access it through dot notation?
No. You should use you should use instead the double square notation.
Okay. Thanks.
So please note that DL list with key head returns a dictionary containing two keys, prev and next, and two corresponding values, none and tail. So if we want to access to this pointer, we need to specify which key we want. So the second key, which is prev. And the same to access tail, which is which corresponds to the key next. Okay? Is it clear?
Yes.
Yes.
Yes, Professor.
Yes.
Okay. And now let's define, let's create a function to create a new element in the first position. This means that just to be clear, what we have to do is that head must this is what must happen at the beginning. So head must have the next pointer referring to E. E must have a previous pointer referring to head. And tail must have a previous pointer referring to E, and E must have a next pointer referring to tail. Is it clear?
Yes.
Okay. Okay, before insertion, we had that head next pointer referred to tail. And now we must insert E between head and tail. So we must update, we must create the new next and prev fields of the new element, copying from the previous head and previous and next and previous of the other. So remember that we are inserting this element between head and tail. This is the first, this is the first position. No, this is wrong. Okay, so this is wrong, and instead just a moment, please. We must take the old next pointer of head. This was the old next pointer of the head, must become the new element's next pointer, because it must stay in between. The previous is head because we must insert our element immediately after head. This is wrong. The next, this is right, because the next element of head must be the new element. And this is wrong, because I need to take the list of this one. But maybe it's better described here. Just a moment. Okay. Oh, I am using the sorry. Okay, it works. So, first of all, let's examine the effect, and then we go back to the function. The idea is we create a doubly linked list, and we add an element with value 4 as first position. So the head, which has a previous none, will have as next 4. 4 will have as previous head and next tail, and tail will have as previous 4 and next none. Okay? How? First of all, I have to create if the new element is not in the list, we must create a new key, which is the new element, with an empty dictionary as value. And then we must take the pointers. The pointers are the next is the next value of the head, which initially is tail, but in general can be any other node. So we must take the next field from the head, which may be, suppose we want to add another node, let's say 7. Okay, then 7 will have as next field 4, which is the node already in the list. Okay, so the old next of head must be the next of the new node. The previous field of the new node must be head. Always, because we had in first position. Then the previous we must update the previous field of the node which lies immediately after the head, which was immediately after the head. And this is the list head with next. Okay. And finally, we must update the next field of head to take E. Seven. Print. Okay, so now head is next 7. 7 as previous head and next 4. So now the list reads head 7 4 tail. So 7 stands between head and 4. So previous head and next 4. 4 stands between 7 and tail, meaning that previous 7 and next tail, and tail as before has not been changed. Okay?
Yes.
I was reading online that sometimes to create this kind of linked list, they start using objects, like defining the class.
Yes, thanks. Yes, of course.
No, I mean,
yes, but you didn't study object-oriented. You didn't study programming at all. So trying these fundamental topics, I need to use the most basic tools I have at hand. In this class, in class and at home, there is people which does not know what a dictionary is. Of course, we could use objects, but you didn't study programming, and this is the result. I have to use basic instruments. Yes, of course. On the books you will find objects for everything.
Is it easier to work with the linked list if you use objects?
It's not easier. Do you know what object-oriented programming is?
We start now.
So the answer is no. Okay, you are not able to walk. You cannot run. Okay, so this is we are trying to walk. I'm trying to learning you to walk. This is my task. Okay? Okay, so this is how things go if we use a dictionary for implementing a doubly linked list. Tomorrow we'll see how to insert an element in any position, because we don't need to have any particular limitation when inserting new nodes in our linked list, and how to remove, and so on. Are there any questions?
No, there are no questions.
Okay. So we may stop here for today.